Hello students, in this video we are going to talk about asymptotic behavior of solutions of linear system. Okay, what does it mean? So essentially, first of all, let's start with a linear system which is a variable coefficient. Okay, consider the system what is it, x prime equals to a of t times x plus b of t. Clear? And let us assume that x at the point 0 is x naught. Clear? Now for this system, let's say that if there exists a solution, we want to see that what is the behavior of the solution, right? So let's say let y of t, let's call this system as 1. Okay, so let y of t solves 1, so b is a solution for 1. Okay, now our question is this, that let's say that can we say something? See, Picard's existence and actually guarantees that there exists a solution. Yes, and we can actually see from this problem that the maximal interval of existence for this problem is going to be whole of R, right? But the thing is this, so we know that a yt solves 1 for all t, t in R, that is there, given x a and b are smooth. Okay, and b are smooth. So basically, if a and b are continuous, that is more than enough. Are smooth. Let's just put it smooth for now. Okay, it's not a problem. Smooth. Now the thing is, we want to see that what happens to this system, the solutions. Okay, what happens to the solutions? So the question is this. See, existence unit give us a solution. It doesn't tell you what the solution is, or it does not tell you what is the behavior of the solution. So essentially, if we cannot solve the problem, what is the next best thing we can do? We can actually talk about what is the behavior of the solution. So let's say what happens at t equals to as t tends to infinity, whether the solution remains bounded or not, whether it tends to 0 or not. So that sort of questions we are going to answer here. So let's say the question is, does the solution, so basically let's say all or some solution. Okay, so for now I'm just writing it, all the solutions. So in this case it's a unique solution, so all the solutions is just the solution. So basically, let me put it this way, that the question is, if the solution so obtained is bounded, okay, or the questions like this, let's say, or tends to 0 as t tends to infinity. Okay, so why t tends to infinity? That's the question. First of all, let us understand. See, this problem, since the maximum interval of existence for this problem is R, right? So what is the maximum interval of existence of 1? It is R. Clear? Provided a and b are smooth. Since it is R, so you see the thing is, it is valid for all t. So t, as t tends to infinity, also there is a solution, right? Now the thing is this, we want to see what happens to the solution as t tends to infinity. Why? Because you see, if t lies between, let's say, t1, t2. So what is so special about infinity? Why not in some t1, t2, let's say, as some, let's say, why not 100, 1000, 1 million? Yeah, the problem thing is this. If you are fixing t between t1 and t2, this is a compact set, right? This is a compact set. And the solution which you have, y, so let's say y solves 1, right? So y is a C1 function, C1 from R to Rn, right? It's a curve, smooth curve. Okay, it's a smooth curve. Now, since it is C1 from R to Rn, now if I am restricting my t between t1 and t2, so basically y is restricted to this, compact set t1 and t2. What does that gives you? That gives you that there is a maxima of y, right? So let's say y naught maxima, okay, in this compact set. So there is a maxima, there is a minima. So we know that y is bounded in sort of this. But the thing is here, if you are looking at the whole interval, then we cannot say whether they are bounded or not. Okay, and that's the question which we need to answer in this video. Yeah. Okay, so let's look at this. See, first of all, let's look at the, see, our study will be like this. First of all, we are going to start with constant coefficient equation, right? Once we know how to handle constant coefficient, we will go to variable coefficient problem. Is this okay? So let's look at the constant coefficient problem first. Okay, so first of all, consider the problem. Consider x prime equals to x, this question, clear? And let's say that we are also assuming that x0 equals to x1, or doesn't matter, let's say x prime equals to x. This is the thing where a is constant, where a is a constant n cross n matrix. Okay, is a constant n cross n matrix. Now for this problem we know that xt is given by the general solution. Okay, the fundamental matrix times C, and fundamental matrix we know that what is it? It is TA in this case, right? Times a constant n cross 1. This is a constant arbitrary matrix. Okay, constant matrix n cross 1. So we know that any solution looks like this, right? Okay. Now the problem thing is this. See, let's say that if it passes through x0 equals to x0, if x0 equals to x0 given to you, then that will imply that x of t is the unique solution given by e to the power ta times x0. Okay. Now, if we want to understand what is the behavior of the solution, okay, as t tends to infinity, now the question is this: what is the behavior? Is the behavior of the solution as t tends to infinity. Okay, so what is it? See, first of all, e to the power ta, let's just understand that. Okay, this is a n cross n matrix, right? This is a n cross n matrix. Matrix, of course, dependent on t that is there, but basically it's a n cross n matrix for a fixed t, right? Okay, now let's look at the norm of t of a. What is it? So norm of t of a, if you remember, it is always dominated by e to the power norm of a mod of t, right? If you do not, you remember when we defined exponential, this is the thing which we proved. Okay, so this is done in that exponential video, whatever video that is. So the exponential video is done. Exponential property, matrix property. Okay, so this is why we actually showed that this is absolutely convergent the series. Okay, so we have this. Now if this is the case, see, the thing is, and now given a is constant, right? So norm a is fixed. Okay, you remember what is norm a? Norm a, this is matrix norm. Or operator norm, whatever you want to call it, doesn't matter. Matrix norm. You can take L2 norm also, it does not really matter. Okay, so essentially that's basically the same. What I am trying to say is always bounded above. That's the thing. Okay, so it's matrix norm. Now you see, the thing is, and so e to the power norm a mod t, so is fixed. So we can say that norm a equals to, let's say, eta, say some number, right? So it's fixed. If you are fixing the matrix norm, let's say operator norm, then that norm of a is eta, some number, real number. Okay, so what happens? Therefore, hence, so this too implies that any solution x of t, if you take the norm of that, what is it? It is always bounded by, dominated by e to the power ta. So you see, what is x of t? X of t is nothing but e to the power ta times x naught, right? Ta times x naught. This is what? This is a n cross n matrix. This is what? This is a n cross 1 matrix. So norm of xt is always dominated by norm of e to the power ta times norm of x naught, right? We proved this. This is basically kind of Cauchy-Schwarz. That's what we proved. If you remember, when we looked at matrix, this thing, the properties of matrix, then we looked at this type of problem. Okay, this is very easy to prove. It's not a problem. So you please do it yourself if you are not convinced. Okay, but we did it in one of the videos when we talked about exponential. Anyways, so if this is true, so you see what happens is that now e to the power ta, the norm of e to the power ta is dominated by e to the power eta norm t, right? So it is dominated by eta mod t, clear, times norm of x naught. You see, okay, and t, for now, let's just assume that t is positive. Okay, oh, I mean, it doesn't have to be, but let's just, okay, doesn't have. Let's just say it is mod t. Okay, now norm of x naught. Here, if it passes through x naught, then it is always dominated by this. Now you see, norm of x naught is fixed, right? Norm of x naught is not changing, clear? So if norm of x naught is not changing, so essentially what happens is the asymptotic behavior of this will depend on t, you see, or t. So as t tends to infinity, let's say, as t tends to infinity, norm of xt, it is always bounded by norm of x naught, which is, let's say, some constant c times e to the power eta times mod t. Clear? So what happens to e to the power eta times mod t? Eta here it's a positive constant, so it is always dominated by simple exponential. That's the only thing which you can say here, at least this. Okay, but this is more than enough. We just have to see that you can norm of x of t can always be dominated by c times exponential eta t. That's what you need to know. Eta times mod t, sorry, eta times mod t. Okay, so t, yeah. So that is what you need to know. That's all. Clear? So that's the maximum we can say if you have a solution which is like for the homogeneous problem, constant coefficient. Yes, that's the thing we can say. Clear? Now we consider this differential equation. So consider the system. Consider the system. What is the system? X prime of t equals to a. I am just changing this system a little bit. So you see, this is a plus bt times a constant matrix x. Clear? Here I will again assume that of course a is a constant matrix, right? B is continuous. Is a n cross n matrix, with continuous entries. Continuous entries. Okay, entries bij, whatever it is, bij of t. Okay, so now the thing is this. You see, this type of system, this is called a part-out system. Part-out system. Is this okay? We'll just call it for namesake. It's not anything special, but we'll just call it like that. Yeah. So let's just call it as 2. This is the system 2, part-out system. Yeah? And how is it part-out? It is, see, A, the matrix A is part-out with A plus BT. Yeah? Constant coefficient matrix, but I'm just part-outing it with a variable coefficient. That's the thing. Now the thing is, we want to see what happens to the solution of this problem. Yeah? Okay. So the first thing is this: we want to find out the sufficient conditions on B of t, so that all solutions. You see, I am not putting any initial data, so that is why I am writing all solutions. If there is the initial data, then you will have a unique solution. All solutions, okay, of 2 remains bounded. So let's look at that theorem. Okay, so theorem 1, let's call it theorem 1. Let all solutions of, let's call this a homogeneous problem, this problem. Okay, maybe I can write it here. X prime equals to ax. This is the original equation, right? The constant coefficient homogeneous equation, and I am part-timing it. 2 is the part-out equation. Let's call this a maybe star. Okay, homogeneous equation, constant coefficient. So let all solutions of star be bounded. Okay, so this is our assumption. We don't know whether they are. Let's just assume that in 0 infinity, open 0 infinity. So basically now we are not looking at t negative or anything, it's only t positive. Let's just understand, because see, our goal is to find out what happens as t tends to infinity. You can do the exact same sort of analysis as t tends to minus infinity, so it's not a problem. Okay, so in that case you just look at minus infinity 0, that's it. So let all solutions of the differential equation is bounded in 0 infinity. Then all solutions of 2 are bounded in 0 infinity. One second, let me just put it this way. Okay, 0 infinity. Okay, maybe I will put it continuous entries in 0 infinity. Let's just put it this way. Okay, so bounded in 0 infinity provided 0 to infinity norm of b s ds is finite. Is this okay? Fine. So we have to prove it. What is the theorem says? It says that if all solutions of the homogeneous problem, see, the homogeneous problem has many solutions, right? Okay, once you put an initial data, then the solution is unique, but generally speaking, it has many solutions. Okay, now what it is saying is this: if you are interested in looking at the what happens to the solution of the Patab equation, you look at the the homogeneous problem. And what we do is this: if the homogeneous problem, if all solutions are bounded, then all solutions of the Patab equations are also bounded, provided that 0 to infinity b of s ds, the norm, is finite. Yeah. So let's look at the proof. What is the proof? The proof is, let's say that what I will do is this: see this part of the equation. So how do I put it? Note x prime t. If you want to write it properly, it is ax plus bt times x, right? Yeah. And let's call this term. So let's call this as small b of t. Okay, so let me write it like this: define small b of t is capital BT times x. See, x is also a function of t, right? So capital B of t times capital X of t, I will just write it as b of t. Clear? So if we do that, then by Duhamel's principle, or variation of parameter, whatever you want to call it, by Duhamel's principle, what do you get? You get that x of t, okay, is e power at times x naught. Where is this coming from? See, this is the solution of this problem provided x0 equals to x naught. Okay, right? So I'm just using that. So xt equals to e power at times x naught, solution of the homogeneous problem, plus you remember the next part is 0 to t e to the power a t e to the power a s b s, this term x of s ds. Yeah, I can write it like this. Now please understand this. This is what is it. Although I have used this formula, this is nothing but this is actually an integral equation. Why equation? See, I have wrote x in terms of x. Okay, so it's not a solution. Don't think of this as a solution. Okay, it is just a equation. Okay, it is called an integral equation. Okay, now what we need to do is this. See, what is this solution? This is any given solution of the system, right? Please understand, what is this solution? This is any given, this is the general solution of the Patab system 2. Okay, xt. So let's call that xg, xgt. So you see, xgt by doing this solves 2. The general solution, right? This is the general solution. We solve 2. Now the thing is this. So if you remember, this is the general solution of the homogeneous problem. See, x naught is nothing. It's like if it passes to x naught, you write it like this, and this is the particular solution, right? Okay, so it solves 2. Here, now you see that since all solutions of this problem, the homogeneous problem, this problem, so x prime equals to ax, this is bounded, that is given, right? All solutions are bounded. Since all solutions of x prime equals to ax are bounded. Clear? There exists C then such that supremum of T positive, norm of e to the power at is C. Is this okay? It has to be, right? See, if they are bounded, see, x naught doesn't matter. X naught is some, it can pass through any point. It's basically an arbitrary number, right? X naught can be, I can change it to x naught plus delta x naught, doesn't matter. The only thing which actually, provides the boundedness is basically what happens to the exponential man. Now, definitely, if all solutions are bounded, exponential, the supremum of e power at as t greater than equal 0, that has to be some constant c, otherwise they are not going to be bounded, right? Okay. Hence, for all t greater than equal t naught, we have norm of xt is less than equal c naught, right? So basically it means that it is, how do I put it, c times norm x naught. See, supremum is c. So this particular term xg of t, if you take the norm, that will be dominated by norm of this power x naught e to the power at times x naught time e to the power at, right, plus norm of integral that term, right? There is triangle inequality. Now this again is dominated by norm of x naught, norm of e to the power at. If you remember, we exactly did the same sort of thing when we studied matrix norms. So this is true. Now you see e to the power at, the supremum of this is c. So this is dominated by c times norm of x naught. So that is what I wrote here. Clear? Okay. So now plus this term plus again, see here this x of t is there, right? Clear? This x of t is there. So this x of t, if I take the norm on both sides, this x of t is again dominated by one second, let me just see. Okay, sorry, e to the power at is the supremum is given by c. So this e to the power at, I can dominate it by c, right? So it becomes c times 0 to t naught, the norm of b of s, norm of x of s ds. This is xg. Okay, the general solution. Yeah, you can write it like this. See, x of s, b of s, and this whole thing is e to the power a t minus s, the norm of this. This is always dominated by c, so I can just write it as c times bs norm of xs. See, this is what I wrote. Clear? I hope this is clear. Okay, so let me make it cleaner. Okay, now what do we have? Once this is true, you see, you have to use, so if you remember properly, we are in what setup? We are in the setup of Gronwall inequality. So please understand what's happening. Once you have this integral kind of equation, what you do is this is also x, this is also x, right? So I have to write it x in terms of x. So basically if I have to take x out, what is happening? You can actually use Gronwall. So basically if you use Gronwall, that will give you x of t is dominated by some c naught. Okay, some c naught, doesn't matter, I mean some constant, times exponential this c times exponential this c times 0 to t norm of bs. One second, there is a small mistake here, ds. Yeah, this I can do. This holds for all t greater than equal 0. Yeah, this is by Gronwall. Again, if you do not remember, first week only when we talked about inequalities, we talked about Gronwall inequality. Okay, so please go check that video, Gronwall inequality. We are just using Gronwall directly and you get this. Okay, now we are done, right? See, we assume that all solutions of x prime ax is bounded. So this is happening. once this is happening, then this also, actually you see, this also says that xt is bounded, right? See, b of t, if you look at the whatever is assumption is 0 to infinity norm BSDS is finite. So this part is finite. This is just a constant. So exponential some constant term, finite, right? So norm xt is always bounded, and this is for any solution. Please remember this. Okay, one thing I only need to clarify. Need this. You need to clarify this thing. I am not saying that this bound. Okay, I am saying that if you fix any solution is always bounded by this particular term. This is what I am saying. Okay, so it doesn't really matter what solution you get. You can take any x naught and you get another solution, right? But that solution will again be bounded by this. That's what I am trying to say. Is this clear? Okay, so what did we learn? Very easy. We learned that if you start with we started with this x prime equals to x. Yes, we assumed. See, we don't know whether such a thing happens or not. Let's just assume that by somehow we get to this information that all solutions of this problem are bounded. Once that is there, then you can say that all solutions of this problem bt times x is also bounded. Yeah, but when is it true? If integral bt is finite. Clear? That's what it basically says. Okay, so now let's look at the condition. Now we want to find some sufficient condition on the matrix B of x. Okay, B of x, sorry, B of t, so that all solutions of what did I call this? 2, right? 2 tends to 0. So did you understand the question? See, the thing is, the first thing is this: we wanted to understand that when are all the solutions are bounded. Now that we know that when all solutions of the homogeneous equations are bounded, then all solutions of the part equations are bounded, provided that the B is basically integrable. Okay, norm of B. Now the question is this: when can we say that all solutions of this matrix BT they tends to 0? Okay. So let me ask you this question. Maybe you can pause this video and think about this. When do you say that all solutions of these Butterfly equations tends to 0 as x tends to infinity? Okay. So the theorem, I want you to maybe you can think about it yourself. Okay. So pause this, do that, and then come back. So see, let all solutions, again this is exactly the same sort of thing, huh? Let all solutions of x prime equals to ax, this system, tends to 0 as t tends to infinity. Okay, then all solutions of 2 tend to 0 as t tends to infinity. Okay, provided see, initially what did we needed? We needed integral of b of s is finite. Now we need if b of s goes to 0 as, or b of t, maybe I can write it as t goes to infinity. Is this okay? Very, I mean, this is very intuitive, right? It should happen. Okay, but the thing is, I mean, intuition is fine. You have to again, anyways, prove it. But the thing is, this is the, okay, and it is quite intuitive. From the earlier theorem, it is very intuitive. Okay, so let's look at the proof. So first of all solutions of x prime equals to ax tends to 0. That is given to us. Okay, so if that happens, then one can say that, see, let's say, let A be such that all its eigenvalues have negative real part. Okay. If that is the case, now you see, if that is the case, then what can you say? Okay, so if all the eigenvalues have negative real part, okay, then you can see that this is a part of the assignment. Okay, you have to check this part. So check that the solutions, any solutions basically tends to 0 as t tends to infinity. Okay, right. So maybe I can give you some ideas why this is true. Okay, let me give you some ideas. Okay, again, this is not the whole proof. Okay, I'm just giving you some ideas how to go along this. Okay, see, any solution of this, how does it look like? It is basically, let's say lambda 1, A has this eigenvalue. Let's do it for 2 cross 2. Yes, and lambda 2, two distinct eigenvalues. Yeah, I'm doing the easy case. I am leaving the hard case for you. So lambda 1 and lambda 2, two distinct cases. So you have two eigenvectors, v1 and v2, and we know v and v2, they are linearly independent. v1 and v2 are linearly independent. Okay. So what is the solution? x1 of t. What is it? It is e power. Sorry. One second. It is v1 times e to the power lambda 1 t, and x1 is x2 of t. It is nothing but v2 times e power lambda 2 of t. Right. Now, what is the general solution x of t? It is nothing but c1 v1 times e to the power lambda 1 t plus c2 v2 times e to the power lambda 2 t. Clear? Now, if this is the case, so you see that if lambda 1 and lambda 2 are negative, okay, so if lambda 1 and lambda 2 are negative, if both are negative, what happens then? What can you say? See, v1 and v2, then, okay, so let me do it properly. Maybe I can do it properly. Okay, so let us assume that, let me do it here. If A 2 cross 2 matrix has eigenvalues lambda 1, lambda 2, and v1 and v2 are the corresponding eigenvectors. Okay, then the general solution x of t looks like c1 times e power lambda 1 t v1 plus c2 times e power lambda 2 t v2, right? That we know. This is the, you remember the method of eigenvalues when we studied, we exactly did the same thing, right? Now you see, then, so if this is the case, then what is norm of xt? Norm of xt is always dominated by c1 is some constant, right? So let's just put a mod there. Norm of v1, which is fixed. v1 is fixed, it's not changing. And then e to the power lambda 1 t. Right? Okay, sorry, I should not, this is a real number, okay, a positive real number, plus c2 norm of v2 e to the power lambda 2t. Yes, now you see, as t tends to infinity, if t tends to infinity, okay, and lambda 1 and lambda 2 are both negative, let us assume that, what happens to this term? This goes to 0, this goes to 0, and this is always positive, so norm of xt must go to 0. Clear? So if both the eigenvalues are negative, then this is going to happen. Okay, now the question is this: can you do similar thing when you have a repeated eigenvalue, or if you have a complex eigenvalue? So basically, in that case, you have to look at the real part. Yeah. Okay. So I want you to check this yourself. Please do that. Fine. This is one of the part. Fine. Now see. Thus, so what do we have? We have that you have the function, the matrix A has negative eigenvalues, negative real part, that is fine. Then you can actually say that all solutions tends to 0 as t tends to infinity. That is given to us. Okay. So now what we can say is thus there exists c and eta, okay, such that norm of eta e to the power at, sorry, this is dominated by some constant times e power minus let's just call delta times t. Okay, so maybe eta times t is fine. Eta times t. Eta times t. Yeah, did I use eta somewhere? I have used, right? It should not be confusing. I have used eta somewhere. Okay, maybe not, huh? I don't. Yeah, I have used eta somewhere. Okay, e to the power eta t, right? So I mean, if you want, you can do that. But anyways, it's so okay. You see, the thing is, please remember this. Let's say for this case, okay, this is always dominated by, if you take the maximum of lambda 1 and lambda 2, okay, so you can always dominate it by the maximum of this, so minus eta times t, right? If you can see, huh? So that is what eta is, this basically. Okay, now this holds for all t greater than equal 0. Okay, I hope this is clear how this is coming. See, x of t is nothing but e power at times x dot. So essentially, if I am taking the norm, I can take the norm here, and you can see that I can take the, I mean, maximum of that, and then it can be written as c times e to the power minus eta t. Yeah. Why minus? Because see, both eigenvalues are negative. Here, at least the real part. If they are negative, then only this can happen. Okay. So since all solutions tends to 0, so basically the eigenvalues, the real part at least, they have to be negative. Okay. Okay. So that is why it is minus eta t. Is this clear? Okay. Now also see, p of t, this goes to 0 as t tends to infinity, right? So what does it mean? It means that for t, let's say greater than equal, let's just call it t1. Okay, one has norm of bt is bounded by some c1, right? I can say that, see, b of t goes to 0, norm of bt. So it means that it is for sufficiently large t, this has to be bounded, right? Otherwise this is not going to happen, right? So this is there. Therefore, for all t greater than equal to t1, we have norm of xt is bounded by c times e to the power minus delta t minus t naught. Okay. No, here I am assuming t naught to be 0, so t naught I don't need, huh? Where is delta t? Because this what is delta? Eta t, huh? Let's write it as eta t. What's that, huh? Eta t norm of x naught. See here, this thing, this is also true, same equation, right? So this is true. Now if you take the norm, e to the power at is dominated by e to c times e to the power minus eta t, so and norm of x naught, clear? And then I have again this term. So this term, what I can do is, if I remember properly, I should do it like this: 0 to t c times e to the power minus delta t minus s, okay, norm of bs, norm of xs ds. Clear? I hope this is okay. Maybe I have to break it up, huh? I have to break it up because this is for t greater than t1, huh? I see, I only have this estimate for t greater than t1. I don't have I don't know what I have to have a different estimate for t less than equal to t1. So what I will do is, maybe I can write it as t1, and then I will write it as t1 to t c times e to the power minus delta t minus s c1 times norm of x of s ds. Is this clear? So for all t greater than t1, this is dominated by c1, so I can write it as c1. Yeah, and for between 0 and t1, bs is just bs. Clear? I hope this is clear. That is why I just broke it up. Okay, so once that is true, that is basically nothing but, you see, if we define e to the power eta t, I will take it on the other side. Okay, so define w of t to be e to the power eta t times norm of xt. Clear? Therefore, what happens is, therefore, what do we have? Let us just call that, let's say that this particular thing plus c times, so one second, let me just look at it. Maybe this whole thing, let us call this particular thing as c dot, okay, and clear. Let me just do that. So this and this, okay, so let's just write it this way. Therefore, w of t, okay, w of t is dominated by this term c one second, I have to norm of x naught, this term e to the power eta t goes there, and this term, so e to the power eta t, sorry, what is delta? It is eta, no? It's not delta, sorry. This is eta, that is why I got confused. Okay, it's fine. Eta. Okay, so now e to the power eta t I can take everywhere. So this term and this term I will just put it together. Okay, right. Sorry about the confusion. Okay, so this term plus 0 t1 to t c times e to the power eta s. See, eta s, this term, e to the minus eta t goes that way, right? So e to the power minus, sorry, eta s comes here, times b of s, I am looking for this term, okay. So let me write it properly, b of s, x of s ds. So so these two terms together plus c2, let's just call c2 as c1 times c2, or maybe I can, it's okay, t t1 to t e to the power eta s xs, sorry, xs, yeah, xs will be there, no? I am doing some mistake somewhere. No, x of s ds, no? E to the power eta t times norm, see, e to the power eta t times x of s is w of s, right? Sorry. This is what, yeah, there are a lot of terms, right? So I am getting confused. So this is x of s, sorry, w of s ds, yeah, this is okay, right? See, e to the power minus eta t goes that way, right? So minus e to the power minus eta t times xt is w of t, which is this. Now I have e to the power eta s is there. E to the power eta s times norm xs is nothing but w of s. So I just wrote w of s. Yeah? So sorry for the confusion. Yeah? Okay. Fine. Now what does that imply? So this will imply, see, this is nothing but, let's just call it this particular term to be maybe C naught, yeah, and let's just call this term to be C2. Yeah, C1 is already there. Okay, so once this is there, what we can say is W of t is dominated by C naught plus C2 T1 to T W of S ds. Right? I can say it. I hope I wrote it correctly. Yeah, I can say that. Now, of course, again using Rodwell. Now again using Rodwell inequality. As I told you, Rodwell is very, very important. This is one of the reason we have W of t is dominated by C naught times exponential C2 t minus t1. Clear? Yes, this is by Cronwall, and therefore what is x of s, x of t, it is dominated by C naught times exponential C2 minus eta. See, your eta t, that your eta t is there, so minus eta. Okay, t minus C2 times t1. Clear? Now, of course, you can see that as t tends to infinity, C2 minus eta, okay, see this C2, yeah, is C1, see, we can always choose C, I again did some mistake somewhere, one second, huh? This is, yeah, I think it's okay, no? C2 is okay, yeah, it's okay. So I can choose C1 small such that C2 is CC1, right? C2 is defined by CC1, see? Okay, C2 is CC1. So this is sufficiently small, so smaller than eta, right? So C2 minus eta is negative. If this is negative, then this goes to 0, right? And this is positive term, norm xt. So therefore, norm of xt must tend to 0 as t tends to infinity. Is this okay? Right? So we have more or less a very good idea of what is happening right now. Okay. So for a boundedness, you need if the constant coefficient problem has all bounded solutions, then the Pater problem will also have the bounded solution, provided the Pater part, that integral part, is bounded. Again, if it goes to 0, again same sort of thing. All solutions of the original equation has to go to 0, and the Pater part, the norm should go to 0, right? Okay. So let's look at one example of where we can use this thing. So maybe next page, example. So consider this equation: x1 prime x2 prime is nothing but 0 1 minus 1 0 times x1 x2. Okay. So what sort of equation is this? This is a constant coefficient equation. This is constant coefficient equation. And let's look at the Pater equation: x1 prime x2 prime, which is 0 1 minus 1 0 x1 x2 plus the Pater term. This is b, this is a, right? See, that's your a, this is the b, and remember b depends on t. Yeah, so you can, of course, you can do that. So basically, but here in this example, what we are going to do is we are going to take it in such a way that b depends on t, so it's a variable part. Doesn't matter, maybe a, let's just see, and a t plus b, let's just call this times x1 x2. Okay, so this, in this case, this is your b of t. Clear? Okay, so for this problem, for the problem, the constant coefficient problem, right, one can see that the fundamental solution, okay, let me write it this way. Let me do the problem properly. Okay, see here, a is 0 1 minus 1 0. Clear? So you do realize that if you, it is very easy to solve, right? It's not a very difficult problem to solve. I mean, you can use eigenvalues and eigen from vectors, right? And you can solve this problem. So you have to check that cosine t minus sine t and sine t and cosine t forms the fundamental set, forms the fundamental system, right? Fundamental system of solution. These two gives you the fundamental matrix, right? Yes. So I hope this is okay. Yeah. Now also check this part. Check that this proper matrix A sine t minus A t plus b times cosine t, okay, and A t plus b sine t. This vector and this vector A cosine t. See, to be very frank with you, this is one of such, how do I put it, systems which can be solved, okay, right? Variable coefficient, but still it can be solved. At plus b sine t and then At plus b cosine t. This forms the fundamental set of solutions forms the fundamental system for the perturbed equation. Perturbed equation. I did not do it, but you have to check it yourself. Okay. Now the thing is, you may think that how are you going to check this? This is actually not a very difficult thing to do. Okay. If you break this equation up, you see the first equation looks like this. X1 prime is nothing but x2. See, 0 times x1 plus x2. So x1 prime is x2. Only this. And what is x2 prime? X2 prime is nothing but minus x1, okay, plus 2a by at plus b times x2. Okay, this is the system. Now for this system, what you can do is, this will imply that x1 double prime, clear, is x2 prime, right? So if you replace it here, it becomes x1 double prime, clear. See, if you replace it here, it becomes x1 double prime is minus x1 plus this term 2a by at plus b times x2. x2 is nothing but x1 prime. Now you see what actually happens is, this is basically a second order equation. You know how to solve the second order equation. Okay, you can use your basic how do I put it, power series expansion. You can do that, or you can directly put these two fundamental set of solutions in this equation and see that whether this satisfies the equation. Okay, it will be okay. So what I suggest you to do is this: you please check this whether these two forms a fundamental set of solution for this perturbed equation or not. Okay, it will be. So you have to just check it yourself. Just put it directly and calculate it. You can see that these two forms. Okay, now what is the x homogeneous problem? Okay, homogeneous problem xg, let's say, of t. How does it look like? Any solution will look like phi t times a constant matrix C. What is phi? Phi is nothing but cosine t minus sine t and sine t cosine t, right, times C. Is this okay? Yes. Please look at this. See this problem. Therefore, if you take the norm of phi t, yeah, the matrix norm, you can take matrix norm, you can take any other norm, doesn't really matter. But you can of course see that this is going to be bounded for all t. Yeah, this is going to be bounded. So these also you have to check and find out the matrix norm. Find the matrix norm. Okay, I hope you can check this part, right? You just have to check if this is a given matrix, you just find out what is the matrix from this norm of this matrix. Okay, so once this norm is bounded, okay, then all solutions of this problem, how do you show they are bounded? Tell me. You just have to see if the norm of this matrix. So check norm of PT, this is bounded for all t. Okay, you see what is BT? BT is this 0 0 0 2a by AT plus b. Okay, you just find out what is the matrix norm. Again, calculate it, huh? And you show that they are, this is bounded. It's very easy. Why I am not doing it? I just want you to calculate it yourself. Okay, anyways, it is part of the assignment whose solution you will get it, so it is already there, but for now I just want you to do it yourself. Yeah, okay, so it is there. Again, if I am asking you whether all solutions of this problem, the butter problem, they are so basically what did we find out? All solutions of the original equation, the constant coefficient equation, are bounded, right? So what about the butter problem? Butter problem also, since norm of BT is bounded, clear? Since norm of BT is bounded, then all solutions of this problem is also bounded. You don't have to calculate this thing. This is just for your information, okay? But you can directly show that it's going to be bounded. All solutions of this problem. Yes. Now what happens if I ask you whether all solutions of this problem goes to 0 or not? How do you find it? What do you do? What you do is you just find out that all solutions of the original equation must go to 0, and then norm of PT must go to 0. Okay. So anyways, so let's just find out what is it. So let's say that, see, one second, did I do any mistake or something? No, right? I did not do any mistake. Anyway, so let's see. See, norm of PT. Okay, this goes to 0 as t tends to infinity, right? T tends to infinity. I hope you can of course find it out. Why? And you see, it is 0 to t. This is very easy to, I mean, once you calculate it, you can see that this goes to 0. So this is bounded and goes to 0. Okay. So 0 to t, you see, you just have to calculate this thing. Norm of BT, BSDS, let's say, BSDS. If this goes to 0, sorry, this goes to infinity. Okay, let's just check that. See, what is it? It is 0 to t 2a by AT plus b. AS plus B ds, right? Now if you calculate this thing, please I will check this part. It is nothing but log of AT plus B by B square. Okay, and as t tends to infinity, you do realize this is going to infinity, right? So what you can say is, for this problem, okay, all non-trivial solutions, okay, are unbounded. Clear? So therefore all non-trivial solutions are unbounded. Yes, why? Because you see, if they are bounded, let's look at the theorem first. What is the theorem says? See, all solutions are bounded. Of course, that is given. All solutions are bounded for this problem. Okay. But the thing is, you see, then these will be bounded provided 0 to infinity norm BSDS has to be bounded. But in this case, you see, what is happening is this. Where is it? You see, for this problem, what is happening is this. All solutions are bounded. For the homogeneous problem, solutions are bounded. No problem. But B of t, if you look at the norm, you take 0 to t norm of BSDS, that is nothing but 0 to t norm of BS is basically 2a by 2s plus b. You can see that this goes to 0 as s goes to 0. Okay, so norm of BS goes to 0 as t, s goes to infinity. But if you take the integral 0 to t 2a by as plus b ds, then that becomes log of this square, which goes to infinity. So basically all non-trivial solutions are going to be unbounded. Is this okay? So for this system, this is such a system such that the original equation, all solutions are bounded, but the thing is for the butter problem the solutions are going to be unbounded. Is it okay? So with this I am going to end this video.